Today we're working on the stack questions from the LeetCode roadmap. So let's begin with valid parentheses. So given a string S containing just the characters brackets, parentheses, and square brackets, determine if the string is valid. So we want to make sure that all the open brackets are closed off and they're closed off exactly with their counterpart. So for example, the bracket can be closed off with the square bracket. So this is a classic stack question where we create a stack. We're going to use a DQ in Python, which is a double-ended queue. And with the DQ, we're going to always append the next string onto the end of the stack. So basically for the example 2, we're going to get a parentheses and then square brackets and then brackets. So whenever we have a closing one, we're going to pop that from the stack so that the stack will be empty at the end if we have a set of valid ones. However, if we have an invalid one, for example, a parentheses closed off with a square bracket, we're going to return false immediately. So let's start implementing this. We have our DQ already. So for S string in S, let's call this char for character. If the character is one of the opening ones, then we should just always append it to the end of the stack. So if it's in one of these three options, we're going to do stack.append. This is the option to push to the right side of the DQ. So else if it's actually elif in Python. So if it's not one of those, then if it's the closing parentheses, so char equals to the closing parentheses and the length of the stack is greater than 0, and the one that's on top of the stack is the opening parentheses. So stack -1, the last element, equals to opening one. Then what we want to do is pop this opening one. So stack.pop. Pop just removes the very last element or the top element of the stack. So let's do the exact same thing here for the different types of brackets. Opening square bracket, then stack.pop. So finally, let's also do the bracket. So in the else case here, if the character is not one of the opening brackets and it doesn't have a match on the top of the stack, then we should return false because that is an invalid set of parentheses. To return false, in the end, we want to check whether or not the stack has 0 size, which means everything has been popped, every pair has been found. So return blend stack equals to 0. I think that should do it. So DQ, we forgot to append char here. Nice, that's accepted. Let's try running it. Okay, cool. So that was the solution to valid parentheses. Now let's move on to min stack. So in this question, design a stack that supports push, pop, top, and retrieving the minimum element in constant time. So basically we want a stack, but as well as retrieving the top element, we also want to have access to the minimum element in the stack. So the smallest element ever pushed onto the stack, but also in constant time. So O of 1. So in this question, the idea here is to have two different stacks. If we have one stack to get the top element and another one to get the minimum element. That way we can always access the minimum and the top element in constant time. So the tricky part here is actually to push the element, because when we push onto the min stack instead of the normal stack, we want to make sure we're pushing the minimum element in the entire stack, not just the new element. So here, let's create two stacks. So self.stack equals a empty DQ and self.minStack this is going to be another DQ. So when we push an element, the normal stack is just going to append the new val. However, we want the min element. So min element, this is going to equal to val. However, it's possible this one is actually, there's a smaller element that was pushed before, which is going to be at the top of the minimum array. So if len self.min stack, if this is greater than 0, so there exists at least one element in the min stack, and this element is smaller than min element, so and self.min stack -1, -1 is the top element of the min stack, is less than min elem is going to equal to that one. So self.min and self.min stack is going to append this min element. So pop here, we're going to have two stacks in our backend, so we need to pop from the stack and also the min stack. So self.stack.pop. Could pop from both of these stacks here. So top is getting the top element, not necessarily the smallest element. So we're going to use the normal stack. Self.stack. So we're going to return the last element. Stack -1. -1 is the top element, and the get min, we're going to return the top element from the min stack. So self.stack min stack -1. And all of these methods have O of 1 complexity. For example, pushing is just pushing onto the end of the stack. Popping is removing the last element, and top and get min are both constant operations to be the value at the end of the DQ. So let's clean this code up here a little bit here. Min element should equal to min val or self.min stack -1 if the length is greater than 0. So .min stack So this does the same thing. It just checks if the new value is actually the smallest, but only checks if there's at least one other element. So let's try submitting this one. Nice, okay, that worked. So that was min stack, and everything was in constant time. So evaluate reverse Polish notation. So if you guys don't know what Polish notation is, RPM, it's basically taking numbers and also operations in a single array. So for example here, we get 2 and 1 first, and then the operation is plus. So we do 2 plus 1, which is 3. Then we have 3 now. This whole thing, the highlighted text evaluates to 3. We get another 3, and the operation is multiply, so we multiply 3 and 3 to get 9. Okay, so what we want to do is evaluate this into a integer output. So again, this is a stack question because we're going to append slowly to the end of the stack until we encounter an operand. And with that operand, we're going to evaluate the top 2 elements that we have on the stack and then combine them into a single element and then push that onto the end of the stack as well. So we're going to create another stack as a DQ. So for T in tokens, let's say if T is one of the operands, so if T in plus, minus, multiply, or divide. So if T is one of these operands, then we want to do is we get the last 2 elements. So v2 equals to stack.pop, v1 equals to stack.pop. So the reason I'm doing v2 is the second operand. So for example, if we do 2 and 1, let's suppose it's minus here because minus makes a difference. So v2 is the second element, but it's going to be popped first. So 1 is going to be popped first and then 2. That way we have 2 minus 1. Otherwise it would be 1 minus 2. So hopefully that makes sense. So v1, v2, and if t equals 2 plus, then our answer is going to be 2 plus 1. So stack.append v2 plus v1 plus v2, elif t equals 2 minus stack.append v1 minus v2. elif t equals 2 multiply stack.append v1 times v2 and elif t equals 2 divide stack.append v1 divided by rounded down v2. So okay, so else if t is not one of the operands, then the stack should just push the number. If it's not an operand, it's going to be a number, so stack.append t. And in the end, we're going to return the last element on the stack, which is stack -1. So the stack should only have one number at the end because it's a valid reverse polish notation. So -1 and stack 0 is going to return the same thing here. Okay, so we can't do v1 and v2. Oh, we should append t as an integer. Okay, wrong answer. With e negative. Okay, I'm guessing it's because Python rounds down for negative division. So the way to counteract that is to do v1. We cast this float into an integer, and this should round up like C does. Just to explain this, so in Python, -1 divided by 2, this is going to equal to -1, whereas in C, -1 divided by 2, this is going to equal to 0. So that's why we have to do this int casting here, just to get the C division. Let's try submitting this. Nice, okay. So next question, generate parentheses. Given n pairs of parentheses, write a function to generate all combinations of well-formed parentheses. So basically here n is 3, so we want 3 open parentheses, 3 closed parentheses, and we also have to make sure they're valid. So a brute force way is we could just generate all of them and then use what we did in the first question, like validate parentheses to validate the valid ones, but we could also do a backtracking solution to make sure we're only generating valid ones. Okay, so that out of the way, let's do the backtracking solution. So let's create a stack, which is a DQ again. And we should create an answer array. So that way we're going to put all the valid parentheses into our answer. Create our function, let's call it backtrack. We're going to need the number of open parentheses we have right now, let's call that open, and the number of closed parentheses we have right now, so let's call that closed. So closed or closed? Closed, okay. So we have the backtracking function. So if closed equals to n, so if we have 3 closing parentheses, that means we have to have had 3 opening parentheses. So we have a valid one, and let's put that in the answer. So ans.append, let's okay, so ans.append, I believe it's string.join. So we join the stack without any spaces in between. So we just join that as a string and return that, append that to the answer. After that, we can just return out of the function because we don't want to add any more. So if open is less than n, so we still have room to add more open parentheses. Let's add that to the stack. So stack is a global variable that we're going to be calling throughout the function here. So stack.append a open parentheses. Why does LeetCode do this? Okay, so stack.append open parentheses and call backtrack but we have one more open, so open plus one, closed. And stack dot pop. So what we're doing here is if there's room for more open parentheses, we add one to the stack, and then we try it with the backtracking function until we can get a valid one, and then we remove this open parentheses. So we're done trying it. Now let's try the closed one, and we can only do a closed one if there's more open than closed right now. So if open is greater than closed, stack.append the closing one. We want to backtrack again, but this time open doesn't increase by one, closed increases by one, and stack.pop. So after we're done trying this closed parentheses at the start, we're going to remove it. So that should be backtrack, and we're going to call this backtrack function with parameters 0 and 0 because at the start we have 0 open and 0 closed. And after we should just be able to return answer because backtrack should populate answer for us. Let's see if that works. Okay, that's accepted. So this stack approach of doing backtracking functions is just more space efficient because we don't have to pass in the current string as a parameter to the function. So let's try submitting it. Nice, okay, that worked. Time complexity of this question is very difficult to actually evaluate because we're only generating the possible valid parentheses, not all the parentheses, otherwise that would be 2 to the n. So the number of actually valid ones is based on the Catalan numbers, where in the Catalan number formula, n is 2 times the input here. So it's 2 times this n. So yeah, moving on to the next question, daily temperatures. Given an array of integer temperatures that represent the daily temperatures, return an array answer such that answer I is the number of days you have to wait to get the after the ith day to get a warmer temperature. If there's no future day that this is possible, keep your answer as answer I equals 0. So if there's no warmer day after this, for example, the last day, then we're going to set answer of the last day is going to be 0. Okay, so this is a monotonic stack question where we only want to keep track of the number of days that is warmer than. So for example, the second last day, 76, this is warmer than 73, so there's no more point in keeping 73 in our stack. But for example, 72, we want to keep this in the stack because 69 only needs one more day to get 72, which is warmer than 69. So starting off this question, let's create our answer array and let's just initialize that to 0 for nothing in range len temperature. Okay, so, and we also need a monotonic stack. So stack equals to DQ. So we want to iterate to the temperatures from the back to the front because we care about the days after which gets a warmer temperature. So for I in range len temperature is -1, -1, -1. This is just a Python syntax to iterate backwards in an array. So t equals to temperatures of I. Okay, so if this temperature is warmer than the one after it, we don't need the one after it. So for example, 76 is warmer than 73, we don't need 73. So while t is greater than stack -1, again, -1 is the top number in the stack. And this stack, we're going to need to record the temperature and also the index. So if t is warmer than the index, which is I, so this is 0 is the first element, so while t is greater than that, and also we need to make sure len stack is greater than 0. So we're going to want to pop this element from the stack, so stack.pop. So now we make sure the last element, if there remains another element in the stack, that element is going to be warmer than the current day. So min so days until, actually let's just call this hotter day. This is going to be equal to 0 if len stack. So if there is another day in the stack, then that means that day is going to be hotter than the current day. So hotter day equals to stack -1. Stack -1 is the top element, and 1 is going to be the index. So here, answer of I, this is going to be equal to the current day index, which is I, minus, the hotter day index minus the current day index. And then we just return answer. See if that works. Now we're returning a bunch of negative numbers. So T is temperature is I, while len stack is greater than 0, and T is greater than stack of -1, 0. So while this temperature is greater than that, it should be greater than or equals to stack.pop. So we pop that element. So if there exists another day, and answer of I is equal to, it's going to be I. So here we also need to make sure that we are pushing to the stack. So stack.append, and what we want to push is the temperature of the day, which is T, and also the index of the day, which is I. So let's try running that. Okay, nice, that's accepted. It's going to submit that. So this question is going to be in O of n time based on how many temperatures we get, because every operation here is going to be constant time. There is a while loop inside the for loop here, but this is going to pop at most n times, and in total n times. So it's still O of n. So moving on to the next question, car fleet. So there's n cars going the same direction along a 1-lane road. The destination is target miles away. So we're given the position and speed of all the cars, and a car can never pass another car in front of it, but it's able to catch up and drive bumper to bumper at the same speed. So basically, slower cars that are ahead of faster cars are going to block the faster car, so the faster car drives at the same speed as the slower car. So basically, if cars are next to each other driving bumper to bumper, we call that one car fleet. And we want to see how many car fleets will arrive at the destination. So a single car fleet that is not bumper to bumper with any other car is also considered a car fleet. It's a one car fleet. So return the number of car fleets that arrive at the destination. So let's quickly look at the example here. The target is position 12. So the fast car, there's a car at position 10 and it drives at a speed of 2. There's another one at position 8 which drives at a speed of 4. So after 1 second or 1 unit of time, those two cars are both going to be at position 12. Okay, so they're going to become one car fleet. Similarly, the one at position 5 with a speed of 1 and the car at position 3 with a speed of 3, they're going to meet up at position 6, and they're going to both move at the slower speed until they reach the target. Okay, that makes sense. So this question is another stack question where we want to see how many car fleets are going to be at the destination. So first, let's zip these two position and speed together into one array so it's easier. Let's call that cars. This is going to be a list of zip position speed, and let's cars.sort. We want to sort so that we care about the ones at higher positions, so we want to reverse this. Reverse equals true. So let's print cars just to make sure we're doing this correctly here. Sorry, cars. Okay, never mind. Okay, so instead of printing cars, let's just actually try to do it. So for position speed in cars, so what we care about is how long a car takes. So if a car at a higher position takes longer than a car at a lower position, it's going to block the slower car. Sorry, it's going to block the faster car into one car fleet. And in the end, we want to see how many car fleets. So let's create a stack equals to DQ. So time, this is going to be a double, and time is going to store the target. How far we travel is target minus position. And the time is going to be divided by the speed. So if then stack is greater than 0, so if there's another car with a higher position, because we do the higher positions first in the stack, and that car has the same position. So two cars, if they have the same position, they're not going to block each other ever. So if P equals to stack -1, it's going to be 0. So let's, for this DQ, let's store this as a position time. So if they have the same position, they're not going to block each other, so we can continue here. Continue just doesn't do anything if stack is greater than 0, and however, if a car blocks this, so time, if time is, so the time is the time of our current car. If the time of our current car is greater than or is less than or equal to the car in front of us, which is stack -1, 0, we want to continue. This is going to be 1. 1 is referring to time. And if those two are not satisfied, so in this case, they're automatically blocked because two cars are starting on top of each other. And this time, if the car with a further position is going slower than our current car. In those two cases, those two are going to join into one car fleet. But if it doesn't join into one car fleet, we're going to add a new car fleet to the stack. So stack.append, and what we're appending is the position P and the time. So in the end, we want to return how many car fleets there are, which is going to be the length of the stack. Speed, oh, we should do S and P, because position and speed are the names of the inputs. Okay, nice, that worked. And cars is as we want it to be. Just delete that print and go ahead and submit this. Nice, okay, that worked. So moving on to the next question, and the last question, largest rectangle in histogram. So given an array heights representing histogram's height bar, where the bar with the width of each bar is 1, return the area of the largest rectangle in the histogram. So in example 1 here, it's highlighted that this rectangle of area 10, it's a 2x5 rectangle, is the largest. There's another one that's more horizontal, it's a 2x4, that's going to be area 8, so 10 is going to be larger, and there's no larger rectangle other than 10. So there's another example here that shows another histogram where the largest rectangle is a square of area 4 or just a long rectangle of area 4 as well. So in that case, we should output 4. So this is another classic monotonic stack question where we want to be always tracking the tallest rectangle we've seen so far. And if we have a lower one, for example, we go up to 1, 5, 6, and then we reach this 2. 2 is lower than 6. So we should drop all the elements 5 and 6 and continue with the rectangle of area 2 until we see larger ones such as 3. So this is the same monotonic stack idea, but whenever we pop, we want to make sure we calculate the area. For example, this one we need to make sure we calculate the area of 10. So our stack, we want to create a stack as a DQ again. And this DQ, it's going to store elements height and index. And this is going to be monotonically increasing. So our answer is going to be 0, and for I, H, and numeric heights. So let's begin looking at every height from the left to the right. So while there is a higher one. So for example, we're at the 2 here. The previous one 6 and the previous one 5 are both taller. So while len stack, so making sure there's at least one element is greater than 0, and h, the current height, is going to be less than, so it's less than the previous one. The previous one is stack -1, 0, 0 for the height, it's the first element, so 0th index. We're going to get the previous height and the previous index. These are going to be gotten from stack.pop. So basically we pop the element 6 here, but we want to make sure we don't lose that area. So to keep that area, the area is going to be the previous height. So the height is going to be 6 times how far it is from now, which is going to be the current index minus the previous index, which is pre-5. So that's the area, and we want to record that in the answer. So ans equals max the answer and area. So if area is bigger than answer is going to be updated to be that. And after that, we want to push to the stack. So stack.append, we want again the height and the index. Oh, the height is going to be h. So, but in this case, we don't just want to push the current index I, saying there's a rectangle of area 2 starting from I. We actually want to start from the last element we popped, which is 5. So we want to say that there's a rectangle of height 2 starting at the index 0, 1, 2, starting at index 2, instead of the starting at currently index 5, 0, 1, 2, 3, index 4, sorry. So we need the minimum index that was popped from the array. So min index pop, let's just call this is going to be I, and every time we pop something, min index popped is going to be min index popped or previous I. So now we're going to push this min index popped. So after that, we can just return answer, and let's see if that works. Okay, wrong answer for the second test case, we're returning 0. That's because in the second test case, this whole thing is a gigantic monotonic stack, so nothing gets popped, which means we don't calculate any areas. So a simple way to make sure something gets popped is just to add another bar in the histogram with height 0. So height.append 0, we're going to add 0, so that means 0 is going to be shorter than every other bar in the histogram, which means they're all going to be popped. So let's try that again. Nice, okay, that worked. So this just guarantees that we're doing this pop and area calculating logic for every bar, even if the entire if the entire histogram is a big monotonically increasing rectangle. So let's try submitting this one. Nice, okay, that worked. So this question is going to be, the time complexity is going to be O of n. So there is a while in here again, just like the previous questions, but this while will only execute a maximum of n times because we can only pop at most n elements and n elements in total. So in the end, this is still a order of n question. And the space complexity is also of n based on how many elements there are. We can store a maximum of n elements in our monotonically increasing stack. So that's it for this video. Thank you guys for watching, and I'll see you in the next one.